Hello friends, I'm Ram Lakshmanan. So I'm the architect of the Ycrash product suite. So in next 3 days, right, we are going to be talking about JVM performance engineering and troubleshooting, right? Let me give you a little bit background or a history about this very amazing technology. Okay, so friends, Java was invented in 1995, right? Java Virtual Machine came with that on day one of 1995 when Java was invented. But there are a lot of things have been changing around this JVM ecosystem. Let's start looking at it, right? Very briefly, let's look back in history. So initially, JVM was running directly on the operating system, right? There was a bare metal operating system, and then JVM was running on top of it. We were running JVM on top of virtualized machines, right? The VMware kind of solutions. There was operating system, VMware, and then JVM was running on top of it. And then there came containers, right? And then there came containers with orchestration layer, Kubernetes. And then also the cloud also came in between, right? We started running JVM in the cloud. This is how the things have been changing below the JVM. But look what has been happening above the JVM as well, right? In 1995, primarily the Java was invented to run browser-based applications, right? That's what it was initially launched. So we were running applets at that time. Now no one remembers applets, right? But that's what it got started, the JVM. And then we started building web applications on top of Java virtual machines. And after that, it became, we started building service-oriented architecture and then mobile applications, right? Say today, the Android, it runs on a Kotlin, which is basically a Java virtual machine. There I made some minor modifications, but at the end of the day, it is still Java virtual machine. Entire Android runs on JVM, right? And then we are running microservices, then IoT applications. So that if you see, below the JVM, a lot of things have been changing, and above the JVM also a lot of things have been evolving. But the Java virtual machine, this architecture, whatever we are seeing today in 2024, is more or less pretty much the same architecture which was there in 1995. Of course, it has become more robust, more performant, a lot of improvisations have gone in. But this architecture has pretty much remained more or less the same. So if you're going to learn this Java virtual machine, this can be a very great lifetime skill for all of you. Right? It has remained more or less same for last 29 years. It's going to remain like that. And it will be a very valuable skill addition to your career. And not only that, today in Java virtual machine, we have like a 50 plus languages are running, right? Look at these. These are the 50 plus languages. Java is one of the primary language, but along with that, there is Kotlin, Scala, JRuby, Python. So many languages are built on top of it. And when you learn to troubleshoot and when you learn to optimize the performance of Java virtual machine, you can eventually, it means you are able to optimize the application which is running on these 50 plus languages. So this is a very powerful skill, very vital skill for you to have. And this is what we are going to be learning in next 3 days, right? And also, I've been giving this training for last 7-8 years. So easily, like we have trained more than 1,000 plus students have been trained through this training program. And several of them have found this very helpful for them, right? So I hope it will be helpful for you as well, right? With that introduction, let me get started. Let me ask this question to all of you. Say XMX is an argument, is a JVM argument, which defines your maximum heap size of your application. Like you can set your XMX to be 2 GB, 4 GB or 10 GB, whatever the size is. And let's say you are going to set your XMX as 2 GB. Will your Java application consume more than this 2 GB size? You can put it in the chat. You can say yes or no, or what do you think about it? Let me repeat the question. Let's say you're going to set this XMX as 2 GB. Will your Java application consume more than this 2 GB memory? So, okay, so we are seeing People responding. Yes. Vishwanathan says no. Nathan says yes. JV S via NIO. Veera says no. Noble says no. David says no. Kevanathan Masa says no. Ajas says yes. Kevin says yes. Okay. So a lot of we are getting a mixed answer, right? So Ricardo is putting a smiley. Right? Okay. This is good, right? To find the answer to this, you need to understand the JVM memory regions. Right? That's what we're going to explore right now. So in JVM memory, there's two primary regions. One is called as a young generation, and other is called the old generation. We'll talk about these generations in detail in the following slides, but from a high level, whenever I create a new object, let's say as a developer, I'm writing a code, new car, I'm creating a new object, car object. That object goes into the young generation, and with that object is going to be living for a longer period. Then it gets promoted from the young generation to the old generation. So when you define XMX, you are actually setting the size of this young generation and old generation only. After that, there is another region called as Metaspace, right? So the Metaspace holds the metadata definitions which are required to execute your application, like say the class definitions, the method definitions. These kind of definitions which is required to execute your program is held in this Metaspace. And this region is outside of the XMX. So it's going to be, say, suppose you're going to define XMX as 2 GB. And let's say you've defined this Metaspace size. This Metaspace size can be defined by this value, this argument, max Metaspace. Let's say you're going to declare this as an half a GB. Then your Java application will consume more than this 2 GB plus this Metaspace. Is that all it is? No. There is another region, right? Some people call this as native memory. Some people call it as an off heap. There's different names given to it. For our discussion in our session, we will call it by the name others. Right? There's this another region called as others. In this region, a lot more information are stored. Like what are those information are? Right? Look at this. Your threads. Where is your threads stored? Threads are a very vital artifact which is going to execute your application. Where are they stored? Are they stored in this young generation, or are they stored in this old generation, or are they stored in this Metaspace? No, the threads are not stored in any of these regions. They are stored in this others region. They are outside of it. So your limit is going to go beyond XMX. And then in Java, the garbage collection is automatic, right? No longer a developer writes a code to release the objects. So garbage collection is done automatically. That garbage collection needs memory. Where is that memory coming from? That memory is coming from this others region. Okay. And then also, friends, the code that as a developer that I write is not the actual code that gets executed at runtime by the JVM. The JVM is a very mature technology. It goes and optimizes our code at runtime. It does a lot of optimization. It recompiles your code. That's what people call as a hotspot compilation. That is, they optimize the code for better performance. That needs memory. Where is that memory coming from? That memory is coming from this others region. Right? And then your application needs connections because your customers are connecting with you. You need connections. And then your application is connecting with several backend system of records. Those needs connections. Where is the memory for those connections are coming from? So memory for connections are coming from this others region. Right? Then also files, file descriptors. Our application writes into file, reads from the file. Where is the memory for these file descriptors are coming from? They are coming from this others region. And in case if our application is using JNI, Java Native Interface, to talk with native applications, that requires memory. Where is the memory for those JNI is coming from? So they are coming from this others region. So when you define XMX, you are only defining the size of young generation, old generation. But this is the primary region. This is the young generation, old generation is the primary region. You're defining that. But after that, there is this metaspace. After that, we have the thread stack, garbage collection, code generation, socket buffers, file descriptors, JNI, all those require memory, and they are coming this others region. So the answer to this question, yes. Answer is yes. Your Java application will consume more than this XMX, what you have defined. Any questions on this topic, right? What we have discussed here?
I think this is a kind of thing that many people are not aware. I talked with some persons from the operating system that they don't know how this works, or the JVM, and we had like a defined scope between the parameters that it's so the young generation objects and old generation, we had like a tight scope defined for memory for that, but they were complaining that our application was consuming more than that. And then I explained that it was something regarding like the Metaspace and the other parts of the JVM. But maybe I think the Metaspace, I think we can limit it as well, of course. But if you don't limit it, I don't know if it can like blow all of the operating system memory. That I don't know.
So the question is, we can limit this young generation, old generation by XMX, and this metaspace can be limited by this max metaspace size. And then there is separate parameters for each and every one of them. Like say for thread stack, right? There is an JVM argument. Let me open a text editor called as XSS, right? This will define the thread stack size. I can define my thread stack size as 1 MB. That means each and every thread in my application is going to consume only 1 MB of space. If you don't say, it's going to default to the default values, which we're going to look at a little later. So similarly, like for defining the connections and all, those are all kernel parameters. You need to tune it in. Okay. So any other questions on this topic?
What is the recommended size we need to put in for native other memories? So let's say you have a 6 GB RAM. Okay. What is the recommended size we need to put it in others versus XMX and Metaspace?
Okay. So Jag, Jag, your voice is not very clear, but let me rephrase this question so that others can understand. So Jag's question is, let's say your RAM capacity is 6 GB, right? So then what is the kind of the size you want to allocate? What is kind of the thing you want to plan, right? See, if your RAM capacity is 6 GB, what you want to do? When you're planning to size your JVM memory, you want to take 3 components, or actually 4 components into place. First is young and old, right? And then the second is metaspace. And the third is others region. And then the fourth is we need to give some memory for kernel as well, right? So what would be the ideal sizes depends from the application to application, right? But if you're going to give a rule of thumb, you want to follow this 80-20. That is, for kernel, whatever the kernel needs, you want to allocate. I don't know, it could be half a GB or 1 GB, right? Leave it there. So this you may want to keep like 80%. So the metaspace and others together, you may want to leave like a 20% space, right? So this is how you may want to go about it.
Okay. What is the default it will take when we don't mention the metaspace and others?
Okay. So see, for the metaspace, it is actually, if I'm not wrong, it is unbounded. It can expand as much as the RAM can allocate it, right? And for the others, there is no one single parameter it's going to govern you for that. There is no one single parameter which is going to limit the others region. So look at what are the components going into the others region. There's a thread stack. The thread stack is governed by XSS, right? And there is, as far as I know, there is nothing which is going to limit the garbage collection and the code generation. But the socket buffers, you can limit it by the kernel parameter, you limit, or this thing which can limit it. So that is the answer to your question.
I understood that, for example, that you said that the XSS parameter, you get 1 megabyte if you define 1 megabyte. So for each thread, right?
Correct.
Is that right? It means
Correct.
that if the system you have like allocated with 100 threads, you will allocate 100 megabytes to the other location,
Correct.
to the other region.
Yes.
Okay.
So Ricardo, you're 100% right. Let's say this XSS is going to only limit the size of what one thread consumes. If it's 1 MB, let's say your application creates like 100 threads. That means you need 100 MB more. But what if your application creates 1000 threads? Then you need 1000 MB, which is 1 GB. Right? Yes.
That parameter, it's just M or MB? Because it's not clear enough for me.
That is M.
Just M?
Yeah, you can also give MB. Yes, both works.
Okay, what's what? Okay.
Yes.
Is the rule apply for pod also?
Yes, 100%.
Okay.
So is this the maximum you're setting? It's not allocating this per thread.
Yes, this is the maximum setting. It is not allocated. Yes, you are right.
Yes. Okay. Thank you.
Yes, you are right. Good question. See, this is going to be a very fundamental slide. Probably one of the most important slide you want to understand. There's nothing rocket, it's just very basic things, but this is very foundational. On this foundation, we are going to build up our sessions, and as well as this is very important for you to troubleshoot any problem.
Where does the PermGen come into picture?
Okay, that's a good question. So Surendra, is it Surendra asking you?
Yes,
okay.
yes.
See, Surendra, before Java 8, there was a perm generation. After Java 8 came into picture, the perm generation was replaced by Metaspace. Pretty much whatever the perm gen was doing is replaced by Metaspace. So in modern JDKs, the perm gen is removed, is evicted. Perm gen is there only in the older version of JDKs, but the perm gen used to contain the same metadata information what a Metaspace is now doing it for in the modern JVMs. Did it answer your question?
Yeah. So,
Yeah,
so
a lot.
are we going to consider to explain anything about the Java 8, because a lot of our applications, I work for most of the Oracle products, so because still they support only Java 8 or 7. So are we talking?
So see the concepts whatever we are discussing is going to be applicable across the JVM versions, right? If you want to talk about Metaspace, you can just replace it for your case. Just think it as a perm gen.
Okay.
Keep it as simple as that. Yes. Now let's look at how a sample Java program gets executed behind the scenes. Right. So let's now walk through. Let's take a hypothetical Java program. Let's execute it. Let's see what happens at the JVM when your program is getting executed, right? So that this will enhance your understanding of Java execution, right? Okay. So friends, here is a sample program. Let's look at the sample program, right? The class name is called as a simple example. It has a main method. Main method is the entry point to this application. And this main method is calling a method A. Look what is method A doing. The method A is initializing a primitive data type integer, x is equal to 1. And from there it is going on to execute invoke method B, right? Now let's see what's going on in method B. The method B, it is instantiating a complex data type, which is called as a car. It's an object. It is instantiating it. After instantiating it, it's going to invoke a method C. And if you see this method C, what it's doing is it is initializing another primitive data type float, which is called 2.11f, right? That's what it is doing. It is a very simple hypothetical program. Let's see how Java Virtual Machine is going to execute this program, okay? At the very heart of the Java Virtual Machine, we have these three memory regions, right? Young generation, old generation, Metaspace, and then there is this others region. Now, to execute every program, we need a thread, right? Where is thread created? Asking, where is thread created?
Others.
Yes, it is created in the others region. So let's visualize this red arrow as the thread, right? So when this thread is created, this thread is going to be created outside of these three regions. A thread stack is going to be created. You can see it is being created here. When it enters, since the main method is the very first method it's going to enter, the main method is added to this thread stack frame. It's added to this thread stack frame. You can see it's added. Now from here, this thread, this program says go and execute method A. Now thread is progressing to method A. Now it has progressed. Look, when it has progressed to method A, now this method A is added to this thread stack frame. You can see it is being added here, right? And now look at this. Here there is this integer x is equal to 1 is declared. Where is this going to be stored? This x is equal to 1. In which region of memory it's going to be stored?
The young space.
Young space, right? Which is what I would have also told, right? Because all newly created object goes into this young generation. But friends, this is a primitive data type, integer. It's not a complex data type. And also this is a local variable, right? It's a local variable. This is only visible within this method. So all the local variables are stored within this thread stack frame itself, right? Look at this. X is the local variable, so it's stored. Since this is a primitive data type, 1, value is 1, it's also stored here in the thread stack frame itself. It just goes in here. So this is where it gets stored. Now, let's say a thread progresses further. Now it goes to execute method B. See, now method B is added here to the thread stack frame. Now, where is this variable y is going to be stored, and where is this car is going to be stored?
That one should go to the young because it's a complex.
Correct. See, friends, look at this. Since this car is an object, there is a class called as a car. So look at this, what happens? Now this car class object, the class definition, is going to be loaded into this Metaspace. See, this is a car, the meta definition of this car is stored into this Metaspace. But the actual car object, look what's going on, is stored in this young generation. Because it's
one question. With the when you get like a new object, you usually get into young and then old generation. Who is responsible to move these or to tune these moves between the JVM?
Ricardo, I'm going to be answering that when we get into the garbage collection part of it. Okay. So now our object is created here, and since this y is a local variable, it's stored in this thread stack frame itself. Okay? And it's pointing like this. Okay. Now the thread sees, oh, now the C method has to be invoked. Now a C is added here. And here if you see, Z is a local variable and it's a primitive data type, 2.11f. So see, you can see it is added like this here. It's added like this. Okay. So now the thread has executed all the methods in this program. Now there's nothing else more for it to execute. Now what it will do? Now it has to start.
Can I interrupt? Can I ask one question?
Please go ahead.
So you started from the main thread, right? Where is the simple example is loaded? Because we don't, that is also one class file, right?
Correct. Good question. Good question. The simple example is a class. It's going to be loaded into this Metaspace definition. The metadata definition of it.
Okay.
Okay. Okay. So now the thread has executed all the methods in this application. Now it is now it has to start exiting from each and every method. And friends, one thing that I want to highlight here is, you see this thread stack, how far it can grow. It can grow until whatever this XSS limit you are setting. So if you're going to set it as 1 MB, this thread stack can accommodate 1 MB of data. And when it goes beyond that 1 MB limit, that's when you are going to get the stack overflow error. Have you seen the Java lang stack overflow error? It happens because when this stack limit gets exceeded, then what this allocated size is, XSS is, right? Okay. So now the thread has executed all the methods. Now it has to start exiting from each method. Let's see what happens to this thread stack as it exits. Now you can see the thread is now going to start to exit. Look at this thread stack frame. What's going to happen when it's going to leave this method, when it's going to exit this C method. When it exited, the C method is removed from this thread stack frame. And also that associated local variable is also removed. And now here we have this thread now going to exit the method B. Something very interesting happens here. Look at it. When this is going to exit, this B is removed from the thread stack frame. See, look at this. The B and this variable, local variable is removed, but this object remains here. This object remains here. And this will not be removed until the next garbage collection event runs. Only when the next garbage collection event runs, what's going to happen is the garbage collector is going to see, whether there's any references to this object. Is there any references? No. The only reference was the Y, which was pointing before. Now the reference is also gone. Now this car object does not have any more reference. It's an orphan. It's a garbage in the memory. So that's when the garbage collector is going to remove it from the memory. Until then, it's going to be residing here, right? Okay. So now the thread is going to exited method B, and now it is here in method A. It's going to exit method A. Let's see what happens. It exits method A.
So it's removed, it's not moved to the old, right?
No, it will not be moved to old. We'll talk about it more detail. Only if this object has references, and if it's going to be surviving for a longer period, then that's when it gets promoted from the young generation to the old generation. But here it has already become an orphan. It has already become a garbage. It's going to be removed when next garbage cycle runs. Okay. So now here the thread has come to its main method, and it's going to exit this main method. Now let's see what happens. Now it's gone. So now this thread stack has become empty now. Okay. Any questions so far on what we have discussed? Is it making sense?
Maybe something that you are about to mention. What happens to the Metaspace,
yes.
The car object in the Metaspace?
Yes, very good question. So this car object is going to be residing in the Metaspace, right? The JVM, when it's going to run the garbage collection cycle in the Metaspace, right? At that time, what it's going to see is it's also going to look whether there's any objects which is referencing this metadata. Now there is no more. So then it gets removed. This Metaspace, the object from Metaspace gets removed. Okay. So it will also get garbage collected. And friends, if you happen to run on technologies like Groovy, is anyone using Groovy in your application? Or you're using Dell Boomi?
Yeah, I use Groovy, but for specific interfaces that we use Groovy code. to script stuff and to pull out data. Yeah.
Okay, is it running on JVM?
Yes.
Yes. So what happens is Groovy is, and all, typically if you're running on a Dell Boomi kind of a no code, low code platform, they are notorious for creating a lot of definitions in this Metaspace. So they keep on creating a lot of, because the Groovy script, it's a scripted language. For every request, it keeps creating new metadata definitions. So this gets filled up and then gets garbage collected. It goes up and down very frequently in that type of technology. But typically, if you're running Java applications or Spring Boot applications, in those cases, these class definitions are loaded at the time, typically at the class loading time, when their application comes up, and they're resident there. So you don't see much activity in Metaspace. Typically, it is more or less dormant in such type of applications. I'm going to be showing some examples of it in our sessions, which is going to follow, right? Any questions on this executions, what we have discussed? Okay, so since there are no questions, now let's run a simple Java program, and then let's see what happens now, right? See, for this, I'm going to be using a simple and open source project called as Buggy App. So this Buggy App is capable of simulating various type of performance problems for you, right? It's a very simple, very basic, very vanilla application which can simulate various problems for us, right? Let's look at the Stack Overflow error. Now let's look at it, this example. See, this is an open source code. It is available in GitHub, and also it's given to you in this training material. In your training materials, there's this Buggy App. Under this, the source code and the binary is given for you, right? So now, this is a code, open source code from Buggy App, which is going to simulate for us the Stack Overflow error. Look what it's doing. So there is this start method, okay? And here there is this counter, which is initially the value 0. Now it's incrementing the counter. And every 1,000 times when the counter goes, I just print it looped how many times it has print. It just prints the system, nothing else. And then now it comes down, and then it's once again invoking a start method. That means it's going to, then the start method is going to come again. It's going to increment the counter, call it again, just keeps on a loop. So that means think about what's going to happen to your stack frame, your thread stack. The thread stack, what is going to happen? It's going to end up with having a start method in this first stack frame. The second stack frame is also going to have a start method. Third is also going to have a start method. So the start method is going to be there always in your thread stack frame. And when it goes beyond that XSS limit, this thread is going to be resulting in Stack Overflow error. Let's execute it, right? Let me execute this program. I'm running it now. Okay, I ran it. Now you are going to see, look at what has happened. It has resulted in Stack Overflow error. See, Stack Overflow error is the most easiest error to troubleshoot and diagnose, because when it happens, it's going to print the entire stack, the thread stack. Whatever we saw in the stack is going to be printed. This is the topmost method. The next method is also start. You see, the one below is also start. So by knowing this, then I can just go here and then I can fix the problem, right? What's going on here? It's going on infinite recursive looping. So that's why this problem is happening. You can see it is printing the stack trace, so we can know what it is. Okay, friends, look at this. Now this thread was able to go for 9,258 iterations. After that, it crashed with Stack Overflow error. Okay, now let me show you. Let me go here. When I ran this program, I set my XSS as 1 MB. Okay, Now, just for fun, I'll make it as 2 MB. When I make it as 2 MB and run, will I get a Stack Overflow error? Yes, no.
Yeah, it will take longer, but yeah.
How about others? Do you guys think?
It will, but it will after little more time, then it will give stack
Yes.
overflow.
That I think it will always depending on how many threads you have defined on the app, and how much memory you have, and how much loops you are doing, and so how many threads you are triggering to do or to execute actions.
Okay. So now when I do it 2 MB, yes, we are going to get Stack Overflow because there is a bug in the code. There's no termination condition. It just goes on an infinite looping, and then we are struggling with this error, right? So now let me run it. Now when I run it, you can see.
But that will only happen because you don't have like a small amount of threads defined, right? If you have like very small amount of thread, then you will not blow out because you
No, Ricardo.
limit.
No, Ricardo. Here we are taking just one thread.
Just one thread.
Just one thread. It is one thread. So any code that hits on this method is going to result in Stack Overflow error. Even if you allocate infinite, there's nothing called as infinite memory. But even if you're going to allocate 500 terabyte, still after a certain point, it's going to get Stack Overflow error. Maybe it takes longer time for it to crash, but still it's going to crash with Stack Overflow error. So now I ran it.
It means that you with just one thread you could get a Stack Overflow with
Yes.
just one thread.
Yes. Yes, you will get, and that's what you are getting now. I'm running with just one thread. You can
It's
see
a limitation on a single thread, not on the
Correct.
all threads.
Yes. So now when you run here, like say now I ran it. Now it was able to. Typically it depends. Typically, see earlier I ran it with 1 MB. It crashed with 9,000 iterations. Now it is able to go almost 2 times that because I've increased it to 2 MB. So it is able to go more iterations, and then now it is crashed. Still with Stack Overflow error, right? So this is an example of Stack Overflow error and how to simulate it and how to look into that, right? Any questions on this?
So is this XSS 1M, is it a hit trial and error like decide, or we decide how do we decide?
See, that's a good question. What you want to do, right? I don't want to use the word trial and error. What you want to do is you want to run it. Say if you're going to set a very aggressive value like a 250 kilobyte, right, or something like that, and you want to run a performance test and see whether you are getting the Stack Overflow error. If you are getting, then you may want to increase the element, right? So that's how I would go about it, setting this value. Okay. So Vishwanathan is asking a question. When XSS 2 MB is allocated for all threads or just for one thread? See, when you set XSS, it is allocated for all the threads created from the Java virtual machine. It is allocated, the size is allocated for all the threads originating from that JVM. Okay. Any other questions?
Quick question. So when you said it's for all the threads, you mean the 2 MB is per thread, which is applied for all the threads? Or...
Correct. Answer is yes. It is 2 MB is per thread and is allocated for, it's set for all the threads originating from the JVM. So do we need any recommended size? So if you're going to ask me, what is a recommended size? See, once again, it depends on the application to application, right? If some application are doing having very nested structure and having a lot of local revision doing, you may have to allocate more. But typically, 512 kilobytes is good enough for most of the application. That would be my recommendation. 512K. Okay. Okay.
Well, what is the default if you do not define it?
Very good question. The default is, it depends on what version of operating system you are running and what version of JVM you are running. Look at this. If you are running on 32-bit Linux, then the 320K. If you're running on a 64-bit Linux, it is 1024K, right? So it depends on what version of operating system and what version of JVM you're running. Okay.
My question was if the JVM have any control over the timeout of the execution threads, if they are like zombie threads, or if they will be there forever.
See, so the JVM, at the JVM level, there are couple of timeout parameters you can set for the connections, but nothing at the thread level. As far as I know, there's nothing, the timeout you can set at the JVM level for the threads.
So it means as if you run like a thread, and if it went wrong, it could be there forever.
Correct.
And just
Yes,
restart.
100%. Yes. Okay. Any other questions on this topic? Okay. Is number of threads correlated to size? Jag, I'm not sure whether I follow this question.
I think he is maybe asking something that I bring before, that like if you have more threads defined, then you will have maybe more memory allocated between those number of threads.
Yeah, that's what my question. Yep.
Yeah, yes, answer is yes. Say, look at this. Say, when I set XMX as 1 MB, let's say your application is creating 100 threads during a low volume time, right? Low traffic at the night time, then it needs 100 MB of additional space. But let's say during a peak volume time, if your application is creating 1000 threads, then what it needs is 1000 MB, which is 1 GB it needs.
So there is a max thread connection. We'll set it in Tomcat or configuration.
Yes.
So that I need to correlate it. That's what.
Yes. Yes.
The
Correct.
connector, yeah. The
Yes.
connector itself.
Yes. Connector is one area. Sometimes your application can internally create a thread pool. Sometimes you may have scheduled tasks. They have its own thread pool. So those all needs to be factored in. Okay. So J. Martin, you're asking how to fix and avoid this kind of issue in terms of programming practices. You're talking about Stack Overflow error explicitly, Martin?
Yes.
See, these are runtime issues, right? There is no, we are going to be talking about when this kind of surfaces, how we are going to address it once it happens, right? Going about it. So we'll talk about it when you're getting the troubleshooting part of it, which is tomorrow, right?